So for this example, we have that the formula P equals 1/100th a squared plus 5/100th a plus 107 models women's normal systolic blood pressure P at age A. Use this formula to find the age to the nearest year of a woman whose normal systolic blood pressure is 120 millimeters mercury. So for this example, we have to find the values A, for which we have that 0.01 a squared plus 0.05 a plus 107 equals 120, which means you just solve a quadratic, where here, if you want to bring that over, you could turn that into 1/100th a squared plus 5/100ths a minus 13 equals 0, which puts us more in mind of the standard form. And again, I don't like any of these as far as being able to factor or complete the square goes. You can if you really want to try. I don't recommend it. Instead, I like jumping to the quadratic formula, where in this case it's a instead of x, but it has the exact same meaning. We will have that a, it's just going to be a little bit clunkier because small a, big A, that sort of thing. But here, a is going to be equal to the negative version of that value, the coefficient of the linear term, plus or minus the square root of that coefficient squared, minus 4 times this coefficient, 0.01 times that coefficient, which is, in this case, a negative 13, which means that it's nice because we're going to end up adding these two values, so at the very least we don't get complex ages. That would be troubling. Tell us our formula's wrong. And then on the bottom we have 2 times 1/100th. So we can simplify this stuff out a little bit. That negative 0.05 will remain a negative 0.05, very interesting. Plus or minus, in here, 0.05 squared is 0.0025. 4 times 0.01 is 0.004, or 0.04. And multiply 13 by that, and you get 0.052. So you're going to have 0.052 plus 0.0025 to get 0.05225. All over 200ths, which is an answer, but not a very good one. And you can check this on a calculator or whatever computation you like, but that here our value for A, the age, is either going to be negative 38.6 or 33.6, where maybe you believe in reincarnation and you have the high, or I think it's average actually, blood pressure in a previous life, but more realistically, well, you'd say that the age we'd expect is about, if we want to round to the nearest year, 34 years. 34 years of age, that is. And before we finish, we'll get one more, let's say, triangular example. For this example, we have that generally speaking, the size of a screen is given in terms of diagonal length, which can be seen as the hypotenuse of a right triangle formed by the sides and a line segment from opposite corners. Use this to find the size of a screen with side lengths 18 and 24 inches. So we're finishing with something maybe a little bit lighter, certainly a little bit smaller. I'm going to try and draw this to scale, I guess. It's actually pretty close. Maybe. It's about half scale. But anyway, while I'm dealing with the setup here, why don't you just pretend that there's maybe something cool going on that fake little screen there. And anyway, for this, we got to remind ourselves of that Pythagorean theorem, which says that for a right triangle, we have the relationship c squared equals a squared plus b squared, where a and b are the leg lengths, as they're called, the sides that are perpendicular to each other, and c is the one that cuts across that hypotenuse, where in this case we have that a is given by, let's say, 18, and b is given by 24, so we will have c squared equals 18 squared plus 24 squared, and this, it's not quite in mind of a quadratic formula problem, but same sort of thing that we're chasing around here in terms of details with squares, where what we would end up getting, pulling those pieces around, is that C, the size of the screen, would be 30 inches. And this is about where we'll leave off for our quadratics. From this point, we are then going to go on and not quite finish the chapter just yet, but talk about some more general kinds of equations that we can solve.